Hello friends. This video serves as a demo for a project I've spent the better part of a year on, chipping away at a vision I initially figured might only take a few months. It's a tool that's meant to simulate the dynamics of our solar system, with an aim towards accuracy, coded in the simplest terms I could manage, with just C++ and OpenGL. No graphics engine, and only a few libraries for systems that would be projects on their own, like lines in the GUI. The last time I showed off this project, it was just the planets orbiting randomly around the Sun. Since then, I've integrated NASA's SPICE toolkit, which allows the program to access accurate positional data for the planets and moons now featured over certain time periods. Uranus and Neptune take so long to orbit that they only have enough precise data for some of it. The program also features artificial satellites, which can be given a starting position and velocity at some time and return the path the satellite will travel by integrating the classical 1pn approximation of Einstein's field equations using RK4, which allows for much more dynamical orbits than the Newtonian integration and a step closer to modeling real spacecraft trajectories. The program interprets when the satellite will be captured by another body and will display the trajectory relative to that body's motion. This might be all that's required to capture with the moon, but with the target much further away, it might be helpful to use the Hohmann transfer subroutine to get a rough idea of when a fuel-efficient transfer window will open, making planning missions much simpler. But how accurate are these calculations? Of course, a few compromises were made in order to keep computations low enough to adjust things on the fly, not to mention the inherent energy loss from the integration that I have yet to correct for. The only way to know for certain would be to import real spacecraft and compare where they end up. NASA happens to host a website with exactly this kind of data for any satellite I could think of. Let's try Artemis 1, NASA's most recent trip to the moon. It is important to make the step size 6 hours, which the program is hard-coded for. The resulting document must only contain the set of maneuvers the craft made in orbit, followed by as much historical data as wanted, which must encompass the maneuver dates, and be flanked by 3 asterisks. Inserting this file into the code using the init-sat subroutine allows for the program to automatically interpret this into the environment, and abridge the data to hold it in a persistent memory text file. In my testing, I found maneuver delta V drift as much as 400 meters per second, and as little as 0.43, suggesting it's quite incorrect. This is a full mission to Saturn to illustrate how all the tools can be used to make rocket science a little easier. I'm satisfied with my progress, and have many more ideas about increasing the accuracy by guessing energy loss, and constructing smarter algorithms to adjust the time step dynamically, depending on the environment of the satellite. Saturn's rings also don't cast a shadow. They used to. The planet's axis should also be oriented on the plane of the moon's. I could go on. Thanks for taking time out of your day to enjoy this presentation. The source code is on GitHub in this video's description.